Hi everyone, this is Professor Herring. Welcome back. Today we're going to discuss the periodic properties of the elements and the periodic table. Specifically, we're going to go in depth on learning objectives 1 through 6 for Chapter 4. Please pause the video at this time to read over the learning objectives and make sure that you understand the things that we're going to be discussing today. Understanding the patterns in electron configurations helps us to understand the structure of the periodic table. We discussed in previous videos about electron configurations, and so we're going to go in on how that helps us understand the properties and the elements of the periodic table. Elements within similar regions of the periodic table will have similar properties. Using the locations of elements on the periodic table, we can understand trends. These include atomic and ionic radius, ionization energy, and electron affinity. These are fundamentally based in the effective nuclear charge. Understanding these properties helps us to understand chemical properties such as bonding and reactivity. So the things that we've developed over the past few lectures is going to help us to understand how elements react, which ultimately is the whole purpose of chemistry. We can begin to think about these properties varying as a function of their size and the shape of their orbitals, and also the atomic number, or the effective nuclear charge. In this lecture, we're going to look at several properties of elements, specifically atomic radius, ionization energy, and electron affinity, that can be understood in terms of the electron configurations and quantum numbers. Since the periodic table is based upon electron configurations, we see that these properties can often be predicted by the location of an element on the periodic table. If we take a closer look at the periodic table, we see that the elements are laid out in rows, also called periods, which correspond to the electron shells within an element's electron configuration. The columns on the periodic table are also known as groups or families, and these elements often have similar properties. Elements that are metals are found on the left side and middle of the periodic table. In this region. Metalloids are somewhere between metals and nonmetals, and the nonmetals inhabit the right side of the periodic table. Metalloids are found along this staircase line, and that represents the boundary between metals and nonmetals. Again, elements that are in the same family or group, column, are going to have very similar properties. The first property that we're going to examine is the atomic radius. Before we do so, however, we need to clarify what we mean by atomic radius. The, quote, edge of an atom's electron cloud is actually difficult to pinpoint specifically, since the probability distributions that describe where the electrons reside approach zero as the distance from the nucleus increases. And that makes it difficult to say exactly where an atom ends. But there are two commonly used conventions to describe the radius of an atom, which are described on this slide. The first, the one on the left, is called the non-bonding radius, also known as the van der Waals radius. This value, which is represented as R sub n, represents half of the closest distance between the two nuclei of two free atoms when they collide with each other. So imagine that you have two billiard balls from a pool table and they are just touching each other. If you measure the distance from the center of one billiard ball to the next, that would be the corresponding distance between two elements. That is the non-bonding radius. The second convention, which is here on the right, is known as the bonding radius. And this we can see is smaller than the non-bonding radius, and that's when we have overlap between the electron clouds. It's impossible to really describe this in terms of billiard balls, except if you imagine two billiard balls have smashed into each other, and similar to cars that have crashed into each other, and they've been scrunched up and are occupying the same space. Now that we have identified what the radius is, let's take a look at some trends. These data you can find on the ebook, and the orange line represents approximated effective nuclear charges. Now, we're talking about effective nuclear charge because fundamentally this is the property that dictates almost all of the periodic properties of the elements. So, to understand effective nuclear charge, we want to remember that effective nuclear charge is defined as the atomic number minus the number of core electrons. So, taking this screenshot of a periodic table, the atomic number in this case is indicated by the number above the elemental symbol, and the number of core electrons would be based upon the shell that is up above. So what's not shown here is the noble gases. And so if we have neon here on the right, its number is 10. And so chlorine has a core of neon. We talked about that in earlier videos. If you don't quite remember that, go back and look at chapter 3. And so what we see is that the prediction is that the effective nuclear charge will increase as we go across a period, going from left to right. And then there's a drastic drop-off when we go from the end of one group to the beginning of another group. So when we go from one shell to the next, there's a drastic drop-off. Now, in reality, the actual effective nuclear charges are a little bit off from what we would predict. And we're not going to go into the details of that, but it has to do with the shielding of the core electrons and their interaction with the valence electrons. But what we see is that the trend is that it's generally the same. We have an increase as we go down a period, or as we go across a period, and then a drastic drop as we go from one shell to the next. And we're going to look at this and how this affects other atomic properties. So, as a summary here, we have three basic trends that we can see from the data. One, the effective nuclear charge increases as we go across a row. So as we go from left to right, the effective nuclear charge goes up. The second is that the effective nuclear charge decreases as we move into a new shell. So in other words, as we go down, the effective nuclear charge goes down as well. And then the third one is related to that, and that's the effective nuclear charge going down the column. And let me clarify what is meant between these 2 points here. So this second point is referring to the drastic increase or decrease that we see when we go to a new shell. This third point refers to the difference here. What we can see, these elements here at the beginning represent the elements of the first element within the new shell. And we can see that there's a slight increase in the effective nuclear charge as we go down a column. So, just to clarify, effective nuclear charge increases as we go across a row from left to right, and it increases slightly as we go from top to bottom. Atomic radius is going to follow a similar trend as effective nuclear charge. It increases as we move down a column, and the reason for that is because n, the principal quantum number, increases. The electrons are farther from the nucleus, and therefore they're not held as closely. The atomic radius decreases as we move from left to right across a row. And the reason for that is related to what we just discussed in terms of the effective nuclear charge. Because the effective nuclear charge increases from left to right, the electrons are drawn closer to the nucleus as they experience a greater nuclear charge. This equation you can find in Chapter 2 of the ebook, lesson number 2. It was described by Niels Bohr, and it essentially tells us that the radius is directly proportional to the principal quantum number squared and inversely proportional to the effective nuclear charge. So because the effective nuclear charge increases when we go from left to right on the periodic table, the radius will decrease. Because the n value does not change going from left to right, then that's not going to increase the radius. However, the radius will increase as we go from the first to the second shell to the third shell, etc. So let's see if you've caught on to this. Here are 4 elements, and I'd like you to put them in increasing atomic radius. Pause the video and see if you can do it on your own before watching my solution. All right, so the first thing that you want to do is locate these elements on the periodic table. And then keeping in mind the trends, that the atomic radius decreases as we go from left to right, and increases as we go down a group. All we need to do then is compare. We see that cesium is to the left of barium, and so it should be larger. Barium is below magnesium, and so it should be larger. And magnesium is to the left of chlorine, and so it should be larger. These values here you can find on the ebook, but you are not expected to know them. What you're expected to know rather are the general trends. And so then we can put them in ranked order. Let's now turn our attention to another property called ionization energy. And ionization energy is the minimum energy required to remove an electron from an isolated atom or ion when it's in the gas phase. And in Chapter 2, we talked about how for ionization process that n equals infinity. And what that means is that we've removed the electron from the nucleus. And so now we're going to actually talk about that process and quantifying that. Here are some sample data looking at magnesium. And what we see is that we are pulling an electron away from the element. Magnesium is neutral here on the left. We've removed an electron. Because we remove the electron, it becomes more positive. And we can repeat that process. What we see is that ionization energy is always positive. Therefore, it's always endothermic. What we also see is that ionization energy increases for each additional electron that is removed. So the second ionization energy is always greater in magnitude than the first, and the third is greater than the second, etc. Now, why does this happen? Let's look at it on an atomic scale. So, for the first process, if this is magnesium and we're removing an electron, magnesium has an electron configuration of a core of neon with 3s2. We pull off an electron from the 3s subshell, and now its electron configuration is neon 3s1. What happens is that the electron that is in that third shell was interacting and slightly repelling the other electron in the third shell. And now that it's no longer there, the electron the remaining electron in the third shell is held more tightly to the nucleus. There's fewer repulsions. And so because of it being held more tightly, it requires more energy to remove it. So when we go and we remove that electron, we see that it requires even more energy than the first time. Once it's gone, we have a noble gas electron configuration. And this is important because what we see is that it actually takes a lot more energy to start pulling off electrons from what was the core. And so the energy jump between the second and the third ionizations requires significantly more energy. It was a twofold increase from the first to the second, but approximately a fivefold increase between the second and third ionization energies. And again, the reason for that is because in the second shell, it is significantly closer to the nucleus than in the third shell. And as we've seen in Coulomb's law, where energy is proportional to the product of the charges over the distance, that because now the distance is smaller, there is a greater magnitude of energy or greater attraction between the nucleus and those electrons. And that makes them that much harder to pull off. Therefore, the outer or the valence electrons are always more easily removed than the inner electrons. All right, let's see if you can apply this to a problem. Pause the video now and see if you can solve this on your own. Welcome back. So in this question, we're looking at a plot of ionization energies. And we want to know what element could this be? Well, if you remember from the last slide, we talked about how based on the relative ease or difficulty of removing an electron, that can tell us how many valence electrons there were. So in this particular problem, we see that there are 5 electrons that can be removed easily. It's from the transition of the 5th to the 6th electron removed that requires a lot of energy. Therefore, there are 5 valence electrons. At that point, what you need to do is take a look at the periodic table. By looking at the main group that they are in, you can determine the number of valence electrons. Aluminum is in the 3rd group, and so it has 3 valence electrons. Lithium is in the 1st group, so it has 1 valence electron. Nitrogen is in the 5th group, so it has 5 valence electrons. Helium is in the 8th group, but it's a little bit of an anomaly. It can only have 2 electrons total, so it has 2 valence electrons. And then sulfur is in the 6th group, so it has 6 valence electrons. So the answer in this case is nitrogen. Again, the reason is because we see while there is an increase over time, there's a drastic increase between the 5th and the 6th electron, which means that these all must have been valence electrons, and anything past that would be core. Let's take a look at some more data here. To compare down a group, we want to take a look at elements within the same group. What we see is that the ionization energy is a function of the number of protons. And so going down a group, the ionization energy decreases. The reason for that is because the farther the electron is from the nucleus, the easier it is to remove. Another trend that we see is that going from left to right, that the ionization energy increases. And to see that, you want to look within a given period. Now, there are exceptions to that, and the reason for those exceptions we're not going to go into great detail about. Let's talk more about the rule right now. The reason for the rule, the reason why they increase generally, is that because the effective nuclear charge that the electrons experience increases, and it's harder to remove those electrons. The reason for the variations, these subtle dips that we see here, is due to there being partially filled subshells. The ebook goes into a lot more depth about this, and so if you're interested to know why those anomalies happen, I would encourage you to read the specific section in the ebook that talks about this. Another way of looking at this is the ionization energy as a function of the effective nuclear charge. What we see here is what we just said, that as the effective nuclear charge increases, going from left to right in a period, the ionization energy also increases generally. Another property to discuss briefly is the electron affinity. And this is the process of a gas phase element gaining an electron. Ionization energy was where we removed an electron from the element, and in this case, we're actually gaining the electron. And in most cases, this is going to be an exothermic process. Most elements are able to do this once per atom. In other words, there's only a first electron affinity, not a second or third. And the trend here is a little bit more complicated. If you take a look at these values, we can see that if we look at the absolute value, or in other words, make all the values positive, that we have a decrease in electron affinity in the magnitude as we go down a period, and generally speaking, an increase of electron affinity as we go from left to right. Again, this is in terms of the absolute magnitude. The reason for this is due to the trends in the effective nuclear charge and the number of shells as well. But what you want to be able to recognize here is that this is essentially the opposite process of ionization energy, that for most elements it's negative, but you have several cases where it is positive. And that's here they don't list the values. And the reason for that is because you actually can't measure it if it's not a negative value. And so what this means is that those elements indicated there by the arrows will not gain electrons. The ones with significantly high or significantly negative values, those tend to form stable anions. And so we see that turns out that the elements on the right-hand side of the periodic table, the nonmetals, are the ones that are forming the anions. That's it for this video. In the next video, we'll finish up talking about ions and ion sizes in the periodic table. Thanks for watching. If you have any questions, ask on Piazza or come to office hours. Bye.